This is the 3.5 to 3.8 practice assessment. The first three problems were to determine whether each function is continuous or not at a given point. If it's not continuous, we're going to state whether that discontinuity is a point, jump, or infinite discontinuity. The easiest way to determine real fast whether a function is continuous or not really is to just plug it in and see if you get an output. Now you can plug this in the old-fashioned way and just do 6 squared minus 5 over 6 cubed plus 2, which is going to give you 35 minus 5 on top and 216 plus 2 on the bottom, which, oh, I said 35, when that's really 36. And 36 minus 5 is 31, and 216 plus 2 is 218. Well, as long as I get a real answer out, it must be continuous. The other way that you can do this is you can graph this in the calculator, but you'll need to put those in parentheses, and then go to the table of values and see what answer you get at x equals 6. As long as it doesn't say error, it must be continuous. Number 2, we're going to check x equals 3/2 in the function y equals 5x plus 4 over 2x minus 3. So again, if you plug it in and you evaluate it, that's going to tell you real fast if it's continuous or not. The problem is if it's discontinuous, we got to figure out which type of discontinuity it is. So in the numerator, 5 times 3/2 is 15/2. And in the denominator, 2 times 3/2 is 3. And right away, you should be able to tell, I'm going to get 0 in the denominator of the fraction. Well, if you get 0 in the denominator of the fraction, there's a discontinuity. Now we have to figure out which type it is. A point discontinuity is just a hole. And a hole occurs if you can cancel common factors from the numerator and denominator of a fraction. Well, since this particular function cannot be factored and there's no common factors to cancel, this is not going to be a hole. A jump discontinuity only occurs when you have a piecewise function, and this isn't a piecewise function. So this must be an infinite discontinuity. An infinite discontinuity is also going to occur when you have a vertical asymptote. And how do I find the vertical asymptote? You take the denominator, set it equal to 0, and solve for x. And look, x equals 3/2. The third one here is a piecewise function, but here's the thing. Not all piecewise functions have a discontinuity. If they do have a discontinuity, it will be a jump discontinuity. So if I want to check this algebraically, I'm going to plug in 1 into x into both equations. If they have the same output, then they will be continuous. And if the outputs of each equation are different, it will have a jump discontinuity. Otherwise, you can also graph it in the calculator and see if you see a gap in the graph. A gap in the graph is going to be a discontinuity. But I'm going to show you how to do this algebraically. So 1 squared plus 5 is going to be 6. In the second equation, 3 times 1 minus 2 is going to be 1. Since they have different outputs, different y values, there's going to be a gap in the graph, and therefore there is a jump discontinuity. Again, you could have graphed it by plugging it into the calculator, plugging in y1 equals x squared plus 5, division sign, parentheses, x is less than 1, close it, and then in y2 equals, put in 3x minus 2, division sign, parentheses, x greater than or equal to 1. Remember, the inequality symbols are found under second math. That's the test function. For problems 4 and 5, we're going to describe the end behavior of each equation. Now I can tell you generally what a graph is going to look like just by knowing the largest exponent of x and knowing if that term starts with a positive or negative. Because the largest exponent of x is the 9th power and it's odd, it's either going to have this shape or this shape. This is what it looks like if the leading coefficient is positive, and this is what it looks like if it's negative. Since x to the 9th is negative, this is the general shape. The left side of the graph goes up while the right side goes down. The way we write end behavior, you're always going to start with as x goes to infinity and as x goes to negative infinity. And we're going to determine where y goes. This one is the same as saying the right side of the graph. And this is the left side of the graph. So the left side of the graph is going to go up. So it's going to go to positive infinity. And the right side of the graph is going to go down, so it's going to go to the negative infinity. So this is the end behavior. It needs to be written in this format regardless of how your Algebra 2 teacher taught it to you. Now, I knew what this graph was going to look like without graphing it. Am I telling you not to graph it? No. You, by all means, can go plug this into the calculator and see what the graph is going to look like. And this is the graph you get. And so clearly the left side of the graph is going up and the right side is going down. Now let's work with y equals 3x squared minus 5. First, you're going to set up the end behavior. As x goes to infinity, y goes to blank. As x goes to negative infinity, y goes to blank. The graph of 3x squared minus 5 is just your general parabola that's been shifted up 5 units and has been stretched vertically. It's a parabola that opens up because the leading coefficient is positive, so it looks like this. Both the left and the right side of the graph are going up forever, which means they're both going to infinity, and that's the end behavior. Now let's review intervals of increasing and decreasing. When you look at a graph, first it probably helps if you see the entirety of the graph. When I graphed x cubed minus 6x squared, I could see the top of the graph, or I could see a maximum on the graph, but what I couldn't see was a minimum. So I changed the y minimum until I found this bottom portion here. And it took me a little bit of time. I just kept changing the y minimum value in the window until something popped up. Now that I can see the maximum and minimum, I can determine the intervals of increasing and decreasing. Remember that we read the graph from left to right. And every time we hit a maximum or minimum, the graph changes direction. So from left to right, my graph is increasing until I get to some x value up here, which is at a maximum. So I'm going to use the maximum function to determine where it's at. And according to my calculator, it's telling me it's at 0, 0, which makes sense because if you plug 0 in for x, the output is 0. So if the x value is at 0, then we say the graph is increasing when x is less than 0. The first interval will always be x is less than something. At 0, it begins decreasing. Until where? Well, I need to find that minimum. So now I'm going to use the minimum function on my calculator and find out where the bottom of that graph is at. And it's telling me it's at 4, negative 32. So the x value is 4. So when x is 4, it stopped going down and it'll start going up again. So now the graph is increasing forever, and it's increasing when x is greater than 4. With the intervals of increasing and decreasing, not only do you need to tell me if the graph is increasing or decreasing, but you also need to give me the inequality that represents the x values for which this is occurring. The first interval will always be x is less than a number. The last interval will always be x is greater than a number. Any intervals in between will be compound inequalities. Number 7, y equals the absolute value of x squared minus 4 plus 2 gives you this graph. I actually don't even need to use the maximum and minimum functions to determine the x values at which it stops increasing or decreasing. So from left to right, first it is decreasing. It is decreasing when x is less than, well, it stops at 2, or negative 2, sorry, on the x-axis. And then at negative 2, it starts increasing until it gets to x's 0. So it's increasing from negative 2 until 0. And then at 0, it begins decreasing again until it hits x's positive 2. So from 0 until positive 2, it's decreasing. And then at positive 2, it begins increasing forever. So that's why the last one is x's greater than 2. In number 8 and 9, they want us to name and classify the extrema. Well, if you can tell, the names are already there. The name of the extrema is the ordered pair at which it occurs. So this one says it is at negative 3, 2. This one is at negative 1, negative 3. This one's at 2, 1. And this one's at 4, negative 1. But what will we classify them as? Remember, we have two types of maximums and minimums. The absolute maximum or minimum and the relative maximum or minimum. The absolute maximum or minimum is going to be the absolute highest or lowest point, above which or below which there is no other part of the graph. But if the graph goes up and down forever, any highs and lows are going to be called relative maxes and mins. Well, clearly this graph goes up and down forever. So we call this a relative max. This we'll call a relative min. We'll call this a relative max. And we'll call this a relative min. Number 10 and 11, they want us to determine whether the given critical point is a maximum, minimum, or point of inflection. It's really easy to tell if you just look at the graph of the function. So I graphed x cubed minus 3x, and I want to look at x equals negative 1, which is here. So here's my point. Well, guess what it is? It's a maximum. Number 11, y is equal to x to the 4th minus x squared plus 4 at x equals 0. Well, here's x equals 0. It's a low point in the graph, so it must be a minimum. Remember that a point of inflection looks something like this. The graph doesn't change direction. It continues increasing or decreasing, but it kind of flattens out for a second. We called that a point of inflection. In 12, 13, and 14, we're going to determine any vertical asymptotes, horizontal asymptotes, and holes for each of these functions. Remember that one of the answers could be none. When we do these problems, the first thing we do is make sure that our numerator and denominator are factored if they can be factored. In this case, they are factored. Always look for a hole first. Can you cancel a common factor from the numerator and denominator? If you can, that's going to result in a hole. You determine the hole by taking what you canceled, setting it equal to 0, and solving for x. Remember to put x equals 3 and not just the number 3, or I will not give you full credit. After you determine the hole, then if there's anything else in the denominator, you're going to set that equal to 0, and it's going to determine your vertical asymptote. And it turns out that there is a vertical asymptote at x equals negative 1/2. To determine a horizontal asymptote, you have to think about what the first term would be if you multiplied this out, because this isn't already multiplied out. If you were to FOIL it, the first term would be x squared in the numerator. And if you were to FOIL this, the first term in the denominator would be 2x squared. Since the highest exponent of x in the numerator and denominator are the same, the horizontal asymptote is going to be y equals the ratio of the coefficients in front of those x's. which is 1/2. In number 13, I want you to notice that the denominator is not factored. X squared minus 1 is one of those difference of two squares. It factors into x plus 1, x minus 1. So first we'll look for a whole. Is there any common factor that can be canceled from the numerator and denominator? The answer is no. So there is no whole, and we just write none. The second thing we look for are vertical asymptotes. Remember, you can have more than one vertical asymptote. You set whatever's in the denominator equal to 0, and since there are two factors, we're going to use the zero product property and set them both equal to 0. So x equals -1 is going to be a vertical asymptote, as is x equals +1. The last thing we look for is the horizontal asymptote. The biggest exponent of x is in the denominator. When that happens, the horizontal asymptote is y equals 0. In number 14, this is already factored for us. So let's first find any wholes. There is a common factor that can be canceled. So I will set that common factor equal to 0 and solve for x. And I'm going to find out that there's a whole at x equals -4/5. Since there is something in the denominator that I have not canceled, that's going to give me a vertical asymptote. So I'll now set that equal to 0 and solve for x. And the vertical asymptote is at x equals 2/3. To figure out what the horizontal asymptote is, I have to think about what the first term would be if I were to multiply this out. I don't actually have to FOIL the whole thing out, but if I were to, the first term would be 20x squared in the numerator. In the denominator, the first term would be 15x squared. So the horizontal asymptote is going to be y equals the ratio of the coefficients in front of those terms. But 20 over 15 reduces. It reduces to 4 over 3. So the horizontal asymptote is y equals 4/3. The last thing we talked about was direct, inverse, and joint variation. In problem 15, it says, if y varies jointly as the square of x and the cube of z. I'm going to stop there because the first thing I'm going to do is I'm going to write the equation. It's going to be y equals k, the square of x, and the cube of z. Don't forget the k in these variation problems because that's one of the things that students tend to miss. Well, now that I have the equation, now I'm going to use the givens to find my constant of variation, so I actually find the equation that represents this situation. So it says y equals 81 when x equals 3 and z equals 4. Don't forget, we have to square the x and cube the z. So 81 is equal to k times 9 times 64, and 9 times 64 is going to be 576. And then 81 over 576, let's see if that reduces. It does to 9 over 64. So the equation that represents the situation is y equals 9 over 64 x squared z cubed. Now that we found the equation, now it asks us to solve for the given value. So now I want to find y when x is 10 and z is 4. So y equals 9 over 64, 10 to the second, 4 to the third. And I'm just going to plug this into my calculator, and I'm going to find out that y equals 900. So notice that there are really two answers to this problem. The first thing I had to do was find the equation by first solving for k. And then once I knew the equation, then I could solve for the missing value. In number 16, it says, if y varies directly as the square root of x, and then it starts giving me numbers. So I'm going to stop there. Y is going to vary directly as the square root of x. We gave you a problem similar to this in Algebra 2. It was one of those topics where students kept writing x squared instead of the square root of x, so please be careful when you read the problem. All right, now that I have the equation, now I can plug in my givens. So it says x is 121 when y is negative 9. So I'm going to solve that for k. The square root of 121 is 11. So k must be negative 9 over 11. So the equation is y equals negative 9 over 11 square root of x. Now we're going to find x when y is negative 108. So negative 108 is equal to negative 9 over 11 square root of x. How do I solve that problem? Well, first I multiply the other side by the reciprocal of negative 9 over 11. And I'm going to get positive 132. And then in order to solve for x, you get rid of a square root by squaring both sides. And 132 squared is going to be 17,424. The last problem, it says if y varies inversely as x squared. Y varies inversely as x squared, which means that our input is in the denominator, and it told me that it was squared. Now I'm going to go plug in my numbers so that I can find the equation. So it says y is equal to 12 when x is 4. Don't forget to square 4. This is really just a proportion. So 4 squared times 12 is going to be 192, so k is 192. Y is equal to 192 over x squared. Now I'm going to take that equation and use it to find x when y is 152. So 152 is equal to 192 over x squared. Remember, I said this is a proportion, so if you cross multiply, you get 152x squared is equal to 192. 192 over 152 is going to be, a nasty number, so it's going to be 1.2631579, I'm just going to leave that decimal in my calculator. And if you want to take the square root of the previous answer, what you do is you press the square root key, which is second x squared, and then you press second negative sign. Second negative sign is the answer function. What it does is it'll take the square root of the previous answer. So it turns out that x is going to be plus or minus, remember when you take a square root, we're going to put plus or minus, approximately 1.12. And that is the 3.5 to 3.8 practice assessment.